So good morning. I would like to introduce the IFISC PhD candidate Mirko Goldman, that today will present his thesis entitled Computing with the Dynamical Systems from Implementations towards a Novel Concept. This thesis has been completed under the guidance of Professor Ingo Fischer, Claudio Mirasso, and Miguel Soriano. And I would like also to introduce the members of this of the committee that will examine the thesis. I'm the chair, Sonia Boscolo, and Raul Vicente will act as the secretary of the committee, and Professor Sergei Yamchuk is the third panel member. So before leaving the stage to Mirko, I would like to remind you that after the presentation before we start questioning Mirko, you are supposed not to upload because the examination is still in progress. And you have a chance to leave the room if you wish before the start of the questions. And now, Mirko, it's your turn.
Thanks for the introduction. Today, I'm excited to take you through the journey I've been on during the last 4 years. It's about exploring how we can harness dynamical systems that evolve over time for computations, in particular in the usage for machine learning. This journey starts with photonic implementations, where light becomes the signal carrier, and expands towards novel concepts that will try to push the boundaries of what this system can achieve. But before we start into dynamical systems, I just want to do a quick review of the current computer technology. If you think about computers, you maybe have something like this in mind. Maybe it looks a bit more modern, but actually the idea behind computers has not so much changed in the last years. We use transistors that we compose into logic gates and finally integrate a lot of these things into computer chips. In the recent years, we have advanced this technology from doing just a couple of floating point operations towards doing billions of floating point operations per second. We program these computers to do whatever task we want. So we write instructions like a recipe that in the end allow us to do all these fancy simulations that we physicists like. There's a main idea behind these computers, which is the separation of the memory on the one side and the processing unit on the other side. If you want to operate your computer, you always need to load your data towards the processing unit and store it back. This architecture is usually known as von Neumann architecture. In the last couple of years, we have seen a paradigm shift where we move from logical flows, like programming computers like in recipes, to machine learning. Standard programming usually was good in arithmetic tasks, but struggled with something like image recognition, object detection. Now, machine learning comes into the game and solves these problems. This gives us advanced applications like autonomous driving vehicles. We can predict the folding of proteins, which helps in medicine. And we can nowadays also brainstorm with our computers in natural language. And finally, we get ever and ever more precise and detailed simulations of the world around us. The workhorse of machine learning are neural networks. Neural networks are composed of small subunits called neurons. We have weighted links that lead towards the neuron, and then we have a nonlinear processing unit that can be a tanh or a sigmoid function. A single neuron yet is not that powerful, and therefore we need to compose them into larger networks. So we connect neurons with neurons, and in the end, we feed our data from the left side, propagating to the right side. And we can even make these networks dynamical systems by connecting neurons to each other, and then the signal reverberates within the network. Unlike digital computing, neural networks already do something different. They don't process information in zeros and ones and binary data. They process in the analog domain. And the second distinction is that unlike the von Neumann architecture, where you have the separation of data and processing unit, neural networks perform computations in memory. That means you have the memory stored in your weights and the data flows through that. a network with random connections yet cannot do its tasks, and therefore we need to do learning or optimization of these networks. This can be done as presented on the right side here. So we have some input data that is propagating from the left to the right through our network. We generate some outputs, and usually in supervised learning, you have some targets, so some values that belong to the inputs. You compare them, the outputs and the targets, and you see that there's a discrepancy between what your network predicts and the output. The discrepancy can be described using the loss, and in the last step, you propagate that loss back towards the network, and at every weight, you get a value that tells you how do I need to adjust my weight so that the next prediction is more accurate. While neural networks perform really well in a lot of tasks, they actually apply challenges to the digital computing paradigm. So the miniaturization indicated by Moore's law is slowing down. That means in the next couple of years, we cannot definitely expect that this is further advancing. On the other side, neural networks get larger and larger, having more and more parameters, and the computational power they require, indicated here as petaflops per day, is skyrocketing since the last 10 years. So we can see that the model sizes outpace the compute power that we have at the moment. Furthermore, the von Neumann architecture in the beginning, a really nice idea that allowed to develop powerful computers, becomes into a bottleneck. This is while in the beginning we had program and data still rather small, could easily fit during the save and load through the von Neumann architecture, while now we have larger model parameters, more data, and our architecture here turns into a bottleneck. Finally, all this consumes a lot of energy, and therefore there is a need of more efficient computing platforms. So what if I tell you that the future of computing might not look binary and electronic, but it looks more photonic, exploiting the inherent nonlinear dynamics of photonic devices? It will look more analog, and finally, will ultimately explore and exploit the dynamical of physical systems. How do we get this? Well, I watched machine learning through the lens of dynamical systems. And therefore, we use systems like simple pendulums, recurrent networks, or even lasers with delayed feedback. We can describe and numerically explore these systems with differential equations, and we also can study various dynamics that these systems can give us. But to actually use these systems for machine learning, we need to answer a couple of questions. So before we can use photonic dynamical systems for computations, we need to check what kind of dynamics can we actually use. And in the second step, we want to find out how fast can these dynamics actually be. So what are the lowest timescales we can exploit? In the second step, we're going to look at how to optimize dynamical systems. So how can we, in the learning process, make these systems perform better? And also, how can this optimization process effectively implemented? And in the last step, we're going to look at the generalization ability. Generalization is the main feature of machine learning. It tells you how can a dynamical system or your machine learning system generalize beyond the data it has seen during the training. And we're going to look at how we can improve these abilities. Let me add, the first question we need to answer here is how can we actually make a dynamical system compute? And here, the reservoir computing works as a really, really good starting point. In reservoir computing, we bridge dynamical systems towards a computational task in a quite simple but still powerful mechanism. Our reservoir is divided in three main parts. We have on the left the input layer, where we have our input time series that we map into our dynamical system or feed into our dynamical system using these random input weights. The second part, the reservoir layer, here depicted by a neural network, processes this data in a nonlinear way. And finally, in the output layer, we read out the states of our network and This is the only part we train. So our W out here, our output weights are trained using linear regression, which can be solved in a closed form. Our reservoir thereby has only to fulfill three main conditions. There's one, the echo state property. That means memory fades out over time. We have the separation ability. That means distinct inputs need to lead to distinct mappings. And finally, the consistency, which means that if you have inputs with slight noise on them, still the reservoir needs to respond in a similar fashion. Reservoir computing is that general that it can be applied to any nonlinear dynamical system that fulfills that. So we don't have to use neural networks like in the top. We actually can use a continuous system which has, for example, a delay, is fed by light, or is fed electronically. You can even go one step further. And this is by using a single nonlinearity. And this was developed in-house more than 10 years ago. It's the delay-based reservoir computing concept. Here you use a single nonlinearity that features a delayed feedback. And this is basically emulating a full recurrent neural network. Therefore, we have to pre-process, however, our input. The pre-processing here works as follows. You have your input data S of k that you hold for the input time t. And then each input time t here is multiplied by a so-called mask. The mask acts as the input weights. It can be a random mask. And you see here, it's a step function where each step takes theta time length. Theta is the so-called node separation here. We multiply both signals, the mask and the input signal, and we get this signal which we feed to the network or to our nonlinearity. And our nonlinearity starts to respond in a transient nonlinear way, giving us different node responses at different time steps. Finally, we read out these nodes every time step theta, and then we can again use linear regression to feed our to train our output weights. So now let's get started with the first photonic system. The system we used here is an optoelectronic delay system. It's composed of an optical nonlinearity given by a Marsden modulator. And we have here an optical feedback implemented by a fiber. The signal is afterwards detected, and together with the input, it drives again the nonlinearity. The system can be described using this Ikeda equation, where we have the delay term, the input term, a bias that can be used as a tuning parameter, and the feedback gain. Before we used the system for machine learning, we started to study its autonomous dynamic. That means we ignore the input term here. And if you do that, you can see that for different parameter settings, our system acts differently. So we have here for different feedback gains, fixed point regimes indicated in green. We have a bistable regime indicated in blue. We have a limit cycle regime where we see oscillations between the upper and lower branch in red. And finally, if you increase the feedback gain to a large value, you see chaotic behavior where the system becomes really sensitive to its initial conditions. Now we want to use the system for machine learning. We need to feed it with input data. And the first thing we looked at is driving the system with some time series and exploring how the dynamics look like when the system is fed by inputs. You see on the top the response of the system in the bistable regime here. And you see that actually the input leads to a rapid switching between the upper and lower branch. But still, there are also dynamics that cannot fully describe just by looking at the bistability. If you go to the fixed point regime, you see that your system oscillates slightly around the fixed point here. And if you finally go to the limit cycle regime, you see that there is quite some complex nonlinear dynamics that show some oscillating behavior, but also some more regular, maybe input-related behavior. Nevertheless, for all three regimes, we cannot say that the dynamics are only dependent on the dynamical regime from the autonomous system, nor are they fully determined by the input. So we see a set of new emerging dynamics together with the input. Now the question is, can we exploit these dynamics for machine learning? Therefore, we look at the chaotic time series prediction task, which is given here on the left, which is the Mackie class given by the Mackie class system. We use a part of the data for the training to train our output weights, and then we use the second part of the data for the testing. And we estimate how well our system performs using the normalized root mean square error, which is given here. On the right now, you see we have the bifurcation diagram with our parameter b, which interacts here with the input. And on the bottom, we have our performance dependence on b, the bias, and the input gain gamma. When we start to drive the system weakly with our input, we see that actually only the regime of the fixed point dynamics are usable for computations. So only here around 0.5. The rest of the dynamics leads to weak performance. However, if we increase our input gain, more and more of the dynamics can be exploited for machine learning. And you see that at a certain point, the oscillatory dynamics become quite performant, and also the bistable regime could be used for computations. We find here that the oscillatory dynamics within this regime show the best performance. And we could also find this for various other tasks. And all these results together were summarized in this publication in Chaos in 2023. Now we have determined that optoelectronic or photonic systems can be used for machine learning. We have seen that our system, here evolving in the megahertz timescales, can show different dynamics, but we haven't answered like what is the limit of how fast we can go with our dynamics. While this optoelectronic system lives in the megahertz timescales, we moved on towards an all-photonic system because here we can go up towards the gigahertz timescales. The system works similarly in the reservoir computing with the reservoir computing paradigm. We have our input that can actually modulate neurons at a rate of 80 gigasamples per second, leading to a theta here of around 12 picoseconds. Just for reference, that would emulate almost 80 billion neurons within 1 second. We now feed our data to our system where the delay makes it oscillate in the cavity, and we have our laser that responds to the injected signal. And finally, again, we read out our system's response and train our output weights. We first started to describe the system using the set of Lang-Kobayashi equations, where we have the rate equations of our laser, we have the feedback term with our delay tau, which is around 20.5 nanoseconds, and we have our injection term here, giving the frequency detuning. Now the question arises, can we actually bridge like all the different timescales within our setup? So we have in the beginning the super fast emulation of virtual neurons at 12 picoseconds, but we also have our delay that lives in the nanosecond timescale. And the question is, can we make the system actually performant? The first step we took here is answering the question, can we emulate virtual neurons at roughly 12 picoseconds? Therefore, we went to the strong injection regime, where we can exploit the bandwidth enhancement effect, which was reported in that paper. We see that our response laser starts to oscillate at a high frequency. And if we look closely, we see here our neurons indicated by dots, that the system is able to separate all these states. So first of all, we can get nice signals, well-separated signals, while driving our system that fast. In the second step, we question, can we exploit it for machine learning? And again, we do a parameter scan here using the frequency detuning between the injection and the response laser, and tuning the feedback gain of our delay. And as you can see here, we have different node separations, theta. The feedback is kept at the same length. And now we tune our system, and we see that for all 4 node separations, we see good performance, but also we see that for 12 picoseconds, we actually reach a really high level of accuracy in the Mackie class time series prediction. So those are good indications that our system might be able to operate at these conditions. And the next step is, okay, we can now encode neurons at 12 picoseconds, but we have a delay of 24.5 nanoseconds, which would mean that within our delay time, we can feed up to 2000 neurons, which makes our system quite large. But the question is, do we actually need that size? And also, if our system is that large, it has a rather low input rate. So we cannot feed inputs that fast. On the right plot here, we try to reduce the number of nodes while keeping the node separation and the delay fixed. And what that actually means is that we change the structure of our recurrent neural network. So see here in the bottom, if we have 2000 neurons in our setup, every neuron receives its input one time step into the past. If we change towards smaller number of nodes, we see that nodes get connected and we have a more rich network. And finally, if we go to a really low regime of neurons, you see that the network becomes more or less delay coupled. So every neuron receives a delayed state of another neuron. When we look at the performance, we see that actually, while going towards the delayed coupled network, our performance increases. So we see here that for different frequency detuning, we have our best performance of around 200 neurons. Thereby, we match the timescales of our reservoir to our task. Our task here is to make a class system, which is also a delay system and has some requirements on the memory. We could increase the processing rate from 40 megasamples per second towards 0.4 gigasamples per second. And finally, with this 0.4 gigasamples per second, we reach a power efficiency of 2.6 nanojoules per inference. Finally, with all those results from the numerical side, we went to the experimental verification, which was done or performed together with Irene. And here we measured somehow the same parameter scannings. We have the frequency detuning and also the feedback attenuation. We find similar performance on our Mac class task. And we also can learn a bit more about what happens in our system. So if we look here on the right, we have a frequency detuning of 84 gigahertz, which is somewhere here. And you see that our network responds quite similar. Like all the neurons, the 6 neurons I plotted there, respond in a linear correlated way, which in the end does not lead to high prediction accuracy. However, if we move to better frequency detuning, where the low prediction error is, we can see that the response of our neurons is much more diverse, it's much more nonlinear, and therefore our performance increases. To summarize this part, we showed that reservoir computing can bridge dynamical systems towards machine learning, and that photonic delay systems emulate ultra-fast and versatile recurrent neural networks. We further could show that oscillatory dynamics can be exploited while they were neglected before. And finally, all these results are about matching timescales between different levels in our setup, and this further enhances the computational power of our dynamical systems. So now we have this overview of different levels in our setup. We have the task level, the computing concept, we have our periphery with its modulators, controllers, and sensors. And finally, we have our physical substrate, for example, our semiconductor laser. And within all these levels, there live a couple of timescales and parameters that need to be matched to perform well. While this worked in the examples I showed using parameter scans, it can be a bit more complicated if the system also gets more complex. It's easy to imagine that once you have seen that a single delay system works well, you could compose a network of multiple delay systems and connect them either in row or bidirectionally. Or you could build up a network of delay coupled networks. We saw that they were quite performing well in the Mac class task. And then you get new parameters for all these subunits within your network. Here, the question arises, can we find an efficient way to optimize all these parameters to match like all the requirements and timescales within our setup. The starting point we used so far is reservoir computing. We only train our output weights and leave the rest of the network kind of in a random state. I showed you here on the right side the two performances in two different tasks. We have on one side the MNIST task, which is an image classification. It's here on the top. And we have a time series or sentiment analysis task about movie reviews. So there is plain text that is transformed into a time series, feed to our network, and finally we compute our output weights to decide if this review was in a good or bad sentiment. You see here that the performance of our network increases while increasing the number of neurons. So if you want to have a more performing reservoir, you optimize the parameters, and after you have done that, you can increase the performance by scaling up the size of the network. If we now go to a more rigorous optimization of our network, say we optimize all the parameters, we can compare here the performance in the two tasks. And what we see is that, first of all, the performance improves for all the different sizes. And in particular, it improves for the small sizes. So training our system makes its usage more efficient. And in those two tasks, we find that the factor of efficiency is around 10 to 20 less neurons. This, if you think about a physical system, would mean that we can either have a smaller footprint, we could reduce the energy that the system consumes, or if you think about the delay system, that would mean that we can use it in a quicker way and have a higher input rate. While this system here was trained using the backpropagation algorithm, this is not always usable, especially if you think about physical systems. Well, that's the question, how to train all the parameters. We have here a target system. I was working on that at the Institut Femto-ST in Besançon, together with Anna Scully, who was operating the experiment. The system works as follows. We have laser light that's coming from the left side. We encode an image, for example, from the MNIST data set using binary switches here by DMD. We then can have a couple of parameters that we can tune. Here we use the phase of the light. So we used a spatial light modulator to change the phase. The light was going through a multimode fiber, which randomly scrambled up the information. And finally, we were injecting the signal into a large area VCSEL. That's a laser that has a huge number of modes, and all these modes respond non-linearly to the input. And finally, we can read out these modes, and you can see them kind of as neurons within the laser. Finally, we, in the optical domain, apply the output weights. And here, the output weights could either be, again, mirrors, so zeros and ones, or up to 10-bit 10-bit weights using the spatial light modulator. Finally, the detection at the end of the system is already the prediction. So this system works end-to-end, all optical, and we really receive a prediction from the system. So we don't really need to know what is happening in between. The system can operate really fast. We have 20 kilohertz for the input sampling, and it consumes not much energy because these lasers live in the milliwatt regime. However, there's a big challenge here. Those lasers are really, really expensive to model. And actually, at the moment, there is not really a sufficient model that would give back the dynamics of these lasers. And finally, we have a large amount of parameters in the input SLM and the output SLM that go from 1 to 10 bits that we need to optimize. We now started to think, how can we optimize these parameters? In the first, we define our computational objective. In our case, it was classify images. And then we need to design a program. We need to define what are the inputs, how do we optimize, do we have a model? In our case, we don't have. And what is the parameter space? So in which range can we change our parameters? And finally, how do we determine that our prediction is correct? You now, in general, have these two approaches. You have on the one side the model-based, which uses a model for the optimizer to improve the parameters of your physical system. And on the other side, you have the model-free optimization process, which does not need a model, but usually you need to have more cycles to get towards your desired optimum or your high-performing system. We looked into literature to check what kind of algorithms are around, what can be used from that, and to better classify them, we came up with a set of criteria that I show you on the left. So we have the generality of the optimization, which means how much system knowledge do we need, like how well do we need to model our system. We have the scalability criteria, which means how well does the optimization scale with the number of parameters, how does that affect the convergence time. We have the autonomy, which means how independent is our physical system with its optimization from digital computations. So do we need always a digital computer running on the side of the experiment? Finally, we have the efficiency, which means how long does our algorithm need to run to optimize or to find a solution, and the robustness, how resistant is it to noise, to degradation of the physical system, or to limited resolution of the weights. We looked at those three papers in literature, and we composed them together into this table. Here you can see red. The red color indicates not good aspects, while the green indicates good aspects. And we here stumbled about a problem. And this is for all these three algorithms, we need at least medium knowledge about our system, which we don't have because we cannot fully model the large area pixel in the center of our experiment. So our final solution was to look at search algorithms. Those are model-free optimizations. You don't need any knowledge of your system. It works fully autonomous because you don't really need digital computation on the side of your experiment, and it's robust to changes because it would measure them on the fly. However, it doesn't scale well to a large parameter set because more parameters would mean you need to search a larger space, which is inefficient. And finally, the computational overhead, like the computations you need to do in your physical systems, is quite high. Luckily, our system is super fast. So actually, this term might be compensated by the photonic speed that we have in our experiment. But what about the scalability? Here, we started to look at not simple search algorithms, but evolutionary strategies. That's a topic from reinforcement learning. And you usually there, using evolutionary strategies, you start with a distribution in your parameter space, like your search space in your parameters, which can look like this, parameterized like a Gaussian distribution. So you have a mean and a standard deviation. You now draw examples from your parameter space or your search space here. You compute the error for all of them. And in the next step, you don't update the best parameter set, but you just update the parameter space where you expect that the error is lower. So step by step, you improve your search space, and therefore you get better results. We looked at those two examples. That's the covariance matrix adaptation evolutionary strategy and the parameter exploring policy gradient. They both work in a similar way. Only the difference is that CMAES uses less epochs, has in that sense a quicker update, quicker convergence. However, the computations scale quadratically in the number of parameters, which makes its updates going slower. On the other side, we have the parameter exploring gradient, which needs more epochs, so more updates, but those updates can be carried out faster because we have a linear scaling here. To show how these optimizations work, I have a quick animation where you see in the bottom, in the top left, we have our two initial distributions, and they now start to move slowly towards the minimum here at the center. And the CMAS, as you see, the image or the video is in epochs, converges in quicker epochs. However, PPG also reaches the minimum here And if you transfer this into time, you would see that actually PEPG, since the updates are quicker, can go faster to the minimum. So what we decided now is to use PEPG for going further, because it scales linear in our parameters, and actually our goal was to use a network or a physical system with a lot of parameters. We looked at training the output layer, and we looked at how well it can handle different resolutions of these output weights here. As you see, we started with 2 bits. We reached an accuracy of 80 in the MNIST task. But if we increase the bit resolution, we can, in the beginning, do quite quick jumps up to 88% using 6 bits. However, afterwards, the performance does not increase much. This is not because of the optimization algorithm. Actually, for that task, 6 bits are sufficient. So our system, or the PEPG algorithm, not only was able to train the output weights, it was also able to train with lower resolution and finding good performance here. In the next step, we also included the input weights here. So now our parameter space has has roughly 120,000 parameters. And we have noise in our system indicated here using A. What you see here is when we only train the output weights, the noise is affecting the system performance quite strongly. However, if we move towards training output and input weights, we see that the noise effect kind of cancels out, at least for smaller noise amplitudes. So we here could show that PEPG can train input and output weights. It can handle lower resolution. Here it was 10-bit. And finally, it can also handle noise within the system. And even it finds ways to kind of compensate for the noise in the system. So it seems to be a really strong candidate to optimizing large-scale physical devices in a model-free way. However, so far, we always looked at this as a discrete sampling algorithm. We have our parameter space given here by the dot. We have our mean in red. And then we draw examples from this. And while we were doing this on the experimental setup, I catch the thought that was, what does our system actually do in that sense? So while we move from one parameter set to the other, our system is actually moving around, but it's not moving in a discrete way. Actually, our system is moving in a continuous way, and its state moves continuously. However, because we are coming maybe in our mind from the digital domain, we just think about it as a discrete process. But here, my thought was triggered, and I was questioning, can we actually do this in a more continuous way? So can we connect these points in a continuous way so that we can exploit all the computations our system undergoes? And here the question is, can we find a set of dynamics that perform evolutionary optimization like PEPG, but now in the continuous domain? To answer that quickly, yes, we found a way to solve this. We came up with a solution that uses self-optimizing oscillatory weights that we can formulate here in a set of differential equations. We have our weight, Wi, that is composed of a base, B, and an oscillating term, Vi. Vi, as you can see here, is a oscillation term with its frequency omega I, and it is damped over time using gamma here. We now have our oscillating system, and the idea is we need to find a way to shift the base B towards the optimum, which, for example, in our task here, we would start here, our system oscillates, and we finally want to end up here in the optimum of our landscape. The idea is here that we compare the regional error, given here by E bar, towards a local error, the current error of the system, the current error that our weight is giving us. And we formalized it like that. So if the local error is larger than if the regional error is larger than the local error, our base B shifts towards that local region. And we implemented this here. We tested it on this two-dimensional optimization task. And you see that for different timescales of the error averaging, see that our system in the beginning starts to oscillate and moves towards the minimum. However, with this time scale of 0.1, with this time constant of 0.1, we did not see that our system moves directly to the minimum. It is rather slow and it's oscillating quite a lot. But if we average over larger areas, you see that the system oscillations become a bit larger, but finally also can find the optimum around here. So our continuous dynamics can explore the error landscape and finally also fall into the minimum. And finally, we also check this with neural networks. We have here the iris data set, which is a small data set so that we can use a smaller network, which makes everything a bit more computationally effective. We have our 4 input features. We feed them to our network, let those 70 weights explore the space. And finally, our dynamics were able to optimize for that task. So you see here the initial distribution of your weights, and then they oscillate towards different points that reduce the error and finally increase the testing accuracy in that task. So we really found a way of continuously optimizing a neural network. To summarize it, this part, I've shown that the optimization of information processing related parameters improves the performance and efficiency of our physical systems. I showed that model-free optimization is a really powerful way to do that without having too much model knowledge and works well with the fast sampling of photonic systems. And finally, there's a perspective shift that looking at weights in forms of dynamical systems themselves. All these results were finally summarized in a review paper where there is a section about optimizing photonic physical systems. The last part of my presentation is about the generalization in dynamical systems. And here we have so far seen that we use dynamical systems to perform a single task, for example, time series prediction, but it only showed that it can perform the task it learned during the training. And the question is, can we make our dynamical system generalized towards unseen dynamics? What you can understand behind that question is, for example, we as humans, we can easily interpolate between a walking and running state. And there are a lot of intermediate rays of jogging, fast, walking, and so on. On the other side, dynamical systems parameterized, for example, here, the Mackey class system with its delay tau, can give a range of different dynamics. It can have fixed point, limit cycle dynamics, we can have low dimensional chaotic dynamics, but we can also have really high dimensional chaotic dynamics. And our goal was to make dynamical systems that can generalize to all these different dynamics. We were not the first who thought about this, and there is work about physics-informed machine learning. Here you would either put a prior knowledge of the physics that underlies the task towards the network in form of sending different data, or you pre-configure your data set. You could put an inductive bias on the network topology. And finally, you could also do a learning bias by modifying the loss function. The advantages of this approach are faster learning, you get more precise and reliable predictions, and a higher generalization ability. The first thing we came up with is putting an inductive bias on the network architecture. The network we call now scalable neural networks, and the idea is that we want to predict the size-dependent dynamics of delay systems or spatial temporal systems. On the right, you see a scheme how we would do that. We start with our standard reservoir computing system, and we bias its architecture here in form of the shape, using knowledge about the task we want to do. In the second step, we train our reservoir, we feed it by inputs, collect the outputs, and train the output weights. And in the next step, we would make our system autonomous. In that sense, that means we take our predictions and feed them back as the new inputs. So our network now doesn't receive any inputs externally, it runs on its own inputs. And finally, and this is the new step we wanted to explore here, is the scaling. So while our network is running in the autonomous mode, we scale its size, and therefore we would hope or expect that the dynamics it predicts also change. Our first network that we designed is a delay echo state network, which is basically a standard network, but with the change that the connections between all the nodes here are given using a delay, D here. So all the green connections are delayed connections. We would now train our network and then go in the autonomous mode. So replace the input S of k with our W out xk, so running on its own prediction. We did this first for a quite heavy task, which is the Mackie class task with a delay of 100. This task requires a lot of memory, and usually standard echo-state networks would fail to predict those dynamics. However, here we can show that our network can, on the one side, predict with high accuracy the short-term dynamics. So here you would have the original dynamics and the dynamics predicted by the echo-state network, and they overlay for almost 2,000 steps, while then diverging due to its chaotic behavior. We could see that our network can, to some extent, reproduce the Lyapunov exponent, the largest Lyapunov exponent of our system. And finally, we could also say that in the long term, our network predicts the full high-dimensional attractor of the delay system, as indicated here. So if you compare those two attractors, they look similar. So first of all, we could show that our network can predict long delay systems, but I promised a bit more. I promised that we want to scale our network, and that we did here, changing the delay D from 100 towards 30. So we actually changed the timescales of our network. The hope is now that our system can predict the dynamics of the Mackie class system with a delay of 30, and actually it can. It can really accurately predict the short-term dynamics, as indicated here, and it can also predict the Lyapunov exponent as well as the high-dimensional chaotic attractor, but have never seen those dynamics before and not doing the training. So our network shows high accuracy, but also increased generalization ability. We can also go even one step further. It cannot only predict 100 and 30. If we scale the network step by step, we can reproduce a wide range of different high-dimensional attractors, even intermitting limit cycles within the chaotic regime. And ultimately, we can predict entire bifurcation diagrams. So while our network has learned at the delay of 100, we can scale it in the testing time, and we see that we can recover all those dynamics that are characteristic for the Mackie class system. In the last step, we took what we learned from the delay system and went towards spatial temporal system. Therefore, again, we needed to find a new architecture, which now is composed of parallel networks. And we have our scalable access by adding networks to the side or to both sides and let the network evolve after it is trained. We can show on the bottom here that we train it on a size of 10 pi, but also in the testing phase after the scaling towards 2 pi or 18 pi, the once trained network can predict all these dynamics without having ever seen them. The reason why this is possible is, as we argue in our published paper in Physical Review E, is the time translational symmetry in the delay system or the spatial translational symmetry in the spatial temporal system. You can maybe better understand if you look at these tubes. We have the dynamics plotted along the tube for both the delay and the spatial temporal system, where the circumference is either the delay or the spatial length. And while they are rotating, you see that from all sides, the dynamics are the same, which is indication for our symmetry that we have in the system. And while we scale in our networks those axes, the circumference, our dynamics can also be predicted. Finally, I told you about this human ability of interpolating between walking and running. And this was still an open question to us. So we now could train dynamical system to infer unseen dynamics, but what is if the structure behind our task is too complex or it's just unknown to put it as a bias to our network topology? So what we want to do here is, can we bridge the gap between those two data sets without having any data in between? The idea, and that was in collaboration with Guillaume Pourcel, was that we wanted to use the conceptor framework a explanation of the conceptor framework. It goes as follows. You can see different inputs that go into your network, and your network starts to respond in its state space. You can reduce the dimensionality of the state space using principal component analysis, what I did here. So you have the first principal component and the second one. And now you see that for all the three different inputs with different amplitudes and frequencies, also your state space looks slightly different. You can describe the reverberations of the network in the state space using ellipsoids. And this is basically what your conceptor does. It describes where does your states, where do they reverberate. And finally, once that is captured, you can also use the conceptor to enforce the network to stay within that state space. Our first solution that we came up with is we transferred a normal network into an adaptive network. So we trained our network once using normal reservoir computing, and then in the autonomous mode, we put it in the autonomous mode, feeding back its prediction, but we didn't let our network stay as it is. We plugged in the conceptor. So you see here, that's the network equation with the plugged-in conceptor. And during the network running on its own prediction, we try to force this plugged-in conceptor, so the state space our network is shifted into, using a target. For example, we let our system run with the walking example. It predicts the walking dynamics. But during the conceptor control loop here, we would feed in the state space of the running. So our network would shift towards predicting running dynamics. What we could do with that, well, we could show that the interpolation abilities of our network increased. So we started here with sine waves. You could see that the system can interpolate between sine waves of up to the double of period, while having not trained any periods here in between. We could also show that the robustness of our network increased, so we could cancel out neurons from the network and it still could do its job. And finally, we found a way to use this control loop for signal recovery. All these results were recently accepted in Chaos as a featured article. Finally, we were not 100% satisfied with the performance in the walking and running task. So we needed to come up with another solution. And this is incorporating learning. The idea is here that we perform a recurrent autoencoder where we have our two concepts for walking and running here in blue and green. And those concepts, usually if you start with a random network, are quite far apart. So during the training, we try to enforce those two concepts to become closer and therefore making the interpolation for the network more easy. To do that, we formulated this loss function here, where we have the conceptors of walking and running, C1 and C2, and we performed the backpropagation algorithm, which shows that we can reduce the prediction accuracy, we could increase the prediction accuracy when walking and running. We could also reduce the distance of the two conceptors. And finally, we could close the gap after 400 epochs. So you see here a continuous manifold. Here you have the running dynamics. On the larger circle, you have the walking dynamics. And there's a continuous space between both dynamics now evolving within the network, which is enforced by our training mechanism. And on the right, you see, we actually could not just go to the center and make it jogging. We could continuously control our stickman here to do different speeds in a continuous way. Finally, also those results are now in preparation, where we try to show a two-shot learning algorithm for continuous interpolation using the conceptor-aided recurrent autoencoder. So now we have been through quite a lot of slides. Just to summarize, in the beginning, we started with computing photonic reservoirs. I could show that various dynamics can be exploited for computations. And I also could show that oscillatory dynamics perform well and they were neglected before. So we could add a new dynamical regime to reservoir computing. We showed that we can encode neurons at up to 12 picoseconds. yielding a network that performed close to the gigahertz information processing rates. For the optimization, I could show that full system optimization makes the information processing more efficient. We could increase performance here. And also we discussed that evolutionary strategies are a good way to model-free optimize photonic systems. And we could also show that this is doable in continuous dynamics, not only in a discrete algorithm. Finally, in the generalization part, I showed you that we can exploit symmetries within our task to infer entire bifurcation diagrams that were not shown during the training. And the last part was about the conceptor framework that was used to enhance the abilities of recurrent neural networks and showing complex interpolation of, in this case, motion dynamics. All these results from the part of photonics, dynamical systems, and machine learning were summarized in the last 4 years into 3 main papers and 1 review paper, and there is 1 paper currently in preparation. And finally, and this is the conclusion of my task, I think that the photonic system and the ultra-fast dynamics hold a key for unlocking new physical hardware that can boost the abilities of machine learning, but only we need to consider for that all 3 subjects together in symbiosis. And with that, I would like to thank you for your attention, and I'm looking forward to your questions.